So let us start with the resistance, combination of resistances. So we can combine resistors in series or in parallel. Let's start with the series combination. So in series, what we do is combine resistors like this. So one end of the one resistor is connected to the other end of the second, and then so on. This is R1, this is R2, this is R3, and let's connect it to a voltage source B. So if you want to find the overall resistance of 3, R equivalent or R in series will be equal to R1 plus R2 plus R3, like the sum of the 3. Due to this voltage, current will flow in this from positive to negative, so V will be equal to I into RS, the resistance. Okay.
Yeah.
And then the current in each resistor, current in each resistor will be the same, will be equal, that is equal to I, right? I will flow
Yeah.
here, here and here, but the potential difference across each will be proportional to the resistance value, to its resistance. That is, if it is having a potential of V1, let's say it's having a potential V2, it's having a potential of V3, then V1 is equal to I into R1, V2 is I into R2, V3 is I into R3.
Yeah.
The series combination of resistance. Now let's see what is parallel combination. So in parallel, we are just doing the revision, that's why I'm telling you this fast, because we studied in 10th.
Yeah.
Very easy. Parallel, one end of each resistance is common, they are connected together, and the second end is also connected together, and then this combination is connected across a battery or a cell of V volts. So R1, R2, R3, that's each one having a resistance. So the current that is coming from this battery, let's say it is I, it will get divided into 3 branches. So here there will be current I1, here it will be current I2, and here it will be current I3. The total current I will be equal to I1 plus I2 plus I3, and here it will collect again, and then I will come out, and then it will repeat again. Now in this case, what we can say is that this voltage V, voltage across each resistance will be same or equal, and equal to the V.
Yeah.
connected because each resistance is connected across the same voltage source. You can also draw it like this: 1 R1 on across the same voltage source we connect R2, and across the same voltage source we connect R3. So each one of them is connected across V. Okay, this is also connected across V. This is also,
Okay.
this is the same thing as that, as this thing. Okay,
Yeah.
that's why they will have the same voltage, but the current will be distributed. So I1 will be how much? I is V by R1, I2 V by R2, I3 V by R, and that's why total current I, which is from this equation, total current I should be what? The total voltage on the
Yeah.
total resistance. Let's say the total resistance is Rp, resistance in parallel. Okay, and this is
Yeah.
the first equation. Let's say this is the second equation. Now if you substitute first and second in this, I is equal to I1 plus I2 plus I3, you'll get V by Rp is equal to V by R1 by R2. Taking V common, you'll get, you cancel V, and then 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. That's it. So the parallel combination of resistance will be look like this. You can continue the same way if you have more resistances connected. So it will be 1 by
Yeah.
R4 and then 1 by R5, let's so on. This is the parallel combination, and you already know it.
Yeah.
I'll give you some questions based on it, but will not do it here, or it's related to class 10th. Okay,
Okay.
now we'll start with batteries. So cell or battery. Now we study some internal resistance of a cell.
Okay.
Suppose you draw a cell of EMF E volts, then this cell is not looking something like this only. This is the ideal cell that we should have.
Yeah.
But in practice, what happens is this cell has some chemicals inside it, and due to that, this cell has some internal resistance also. Okay, you might have seen a cell looks something like this, correct? This cell is having a voltage of, let's say, E, but inside it there is internal resistance that we cannot see. It has its internal resistance of its own, so that, let's say, is like this. We denote it with a small symbol, a small r, denotes the internal resistance of a cell. Alright,
Yeah.
this diagram is also drawn like this in books, E comma R, to denote that it has an internal resistance of R without drawing it explicitly. Alright,
Yeah.
and due to this, what happens is when you connect a load, when you connect a load Load means some external resistance. You connect some bulb or something like this to this cell. Okay,
Yeah.
ideal cell would look like this: E and a bulb. This is the ideal cell. In that case, there is current I that will go outside. So I will be equal to E by the resistance of this bulb R. But in practice, we don't have like this. Instead, we have internal resistance R with some E, and that is connected across a bulb. Okay, and the current I is there. Now, what will happen is, see, this is the resistance small r. Now, when the current will flow, this is a capital R. So the resistance drop, the current drop in this will be, sorry, the voltage drop in this resistance would be how much? When the current I will flow in this,
Yeah.
what will be the potential difference across this?
IR.
Yeah, IR, very good. And when it comes here, this small resistance will also give us some drop equal to I into small r, isn't it?
Yeah.
So this is the extra drop, voltage drop that we will get across the cell. Alright.
Yeah.
So in a nutshell, if you see the voltage drop across this cell from here to here, because this all is internal. From outside we can see this and this only. This resistance is internal to the cell. We can
Yeah.
calculate the voltage across this and this end, right? And you
Yes.
can see this is inside the cell. Just a second. Now what happens is that if you put a, let's say you put voltmeter here, okay,
Okay.
across this cell. Voltmeter gives the reading of voltage across that particular branch. All
Okay. Yeah.
right. So what you will get is not the E. The reading of this voltmeter will not be equal to E.
Okay.
Why? Because there is some drop IR that is internal to the cell. What the voltmeter is measuring is it is measuring the voltage drop across this point A and B, let's say. All right.
Yeah.
And this hole is inside of a cell. We cannot go beyond this. We cannot exclude this R and measure the voltage across the this and this, the two ends of a cell, because this all is internal to the cell. We are exposed to this plus and minus terminal of the cell only, right?
Yeah.
So it will measure some voltage, but not that equal to E. It will measure something less than E, so that V would be less than E, because there is some voltage drop that has been dropped here, so that V is equal to E minus this voltage drop IR.
Okay.
This R is the internal resistance of the cell.
Yeah, because it's small.
This R is the internal resistance of the cell. Okay.
Yeah.
Now, one thing, the total
Okay.
current across the whole circuit. Total current is
Yeah.
equal to the total voltage divided by the total resistance. So the total voltage is what? This is the, see, let's draw it again.
Okay.
You have this R you have some external resistance. I have drawn bulb, but it can be any external resistance. This is E, and this is some current that is flowing I, total current of the circuit. And this has a resistance of capital R. Now this current will be equal to, because in a circuit like this where we have two resistance in series, what is the current? E upon R plus R, isn't it?
Yes.
Total current is the voltage, the battery, on resistance. Now if you substitute this value of I in this equation first, all right,
Yes.
then what you will get is you will be able to find a relation, and that relation will give you the value of internal resistance of the cell. I'm not solving it. You will get R is equal to E upon V minus 1 into capital R.
Okay.
This is the formula for, for internal resistance of a cell.
Okay.
Alright.
So I have a question. Why is there a resistance for the battery?
Why is this there?
A resistance for the battery.
This one
Yeah,
is
the
small
internal
r.
resistance of the cell.
This is small r or what?
The small r. Like why is it there for the cell?
It's for everything, cell or battery or whatever. It's internal to the cell. You cannot see. It has not anything is ideal in this world. So this cell should have no resistance ideally. Even a wire should have no resistance, zero resistance. But it does not have a zero resistance. It has some resistance, maybe 0.01 ohm, but that is 0.01 ohm, not zero.
Yeah.
So this cell also has some chemicals inside it, and due to that the hindrance of these chemicals, you get some internal resistance out of that. It's similar to, like, we have not assumed any resistance of this wire. This wire in practice will have some resistance, like 0.01 ohm or something like that. Just there, you cannot remove it. That's so there are two ways. Now the cell can be charged or discharged. So when the cell is discharging means it is giving current, like the current is being drawn from it, like this is discharging. Okay,
Yeah.
we are taking the current out of it. Now in that case you can draw the symbols. So you have a cell and then the internal resistance. Let's say this is point B. Current is going out, so this is I. This is V. No, not V. This is E. This is a small r. Okay. So in this case, the voltage across the points A and B will be, what do you expect? VA minus VB, the voltage across the point. Same, E minus IR.
I.
Voltage across this means there is a voltmeter that is taking the reading. That's it. The voltmeter will take the reading E minus IR. Right?
Yeah, so this is discharge.
This is discharging. Discharging because the voltage is reducing, the current is being drawn. That's why this resistance will dissipate some heat, is equal to IR. Okay, the voltage across this is IR. This will get dissipated. This is not of any use to us, isn't it?
Yeah.
So this is E minus IR, something less than what is E. And during charging, the opposite happens.
Okay.
We supply current to it when we charge it. So which is R, it is E, and the current is being taken into the charge, into the cell. This is A, this is B, this is IR drop. But in this case, VA minus VB would be E plus IR.
Okay.
Okay, because the
Because
current is
current is
being,
being added.
yes, I will see it later. Like we use the Kirchhoff's current law and Kirchhoff's voltage law to do this. Have you know? Have you heard the names?
No.
I will do it later on. So
What is that? Potassium chloride.
these are some laws: current law and voltage law.
Okay.
All right.
Yeah.
So this is a simple combination of the cell. Now let us discuss the combination of cell. So combination of cells like same as that of combination of resistance. So cells can be combined in series, in parallel, or mixed, some in series and other in parallel. Correct?
Yeah.
Why do we need to combine cells? See, we need, suppose a cell is having a voltage of 1 volt,
Yeah.
and the requirement of some load, maybe some bulb or something, is that it requires a voltage of minimum 20 volts to operate. Then either we need a battery of 20 volts, single battery, or we can combine
Sorry.
cells, many cells of 1 volts in series, let's say 20 cells, so that,
Oh, is it like a remote? You put two batteries in it.
yeah, something like that only. According to the load, you change the voltage requirements. So if it's
Okay.
requiring 20 volt, then we need 20 volt. So we will combine whatever we have, we make use of that. So we have 1 volt cell, we will combine them to make a 20 volts. Alright.
Yeah.
So when we combine cells in series, what will happen is we will combine them like this. The internal resistance will also get added up. Okay. So this is E1, R1, E2, R2, E3, R3. And let's say we have n cells like this. Alright.
Yeah.
And then this same is being applied to a load of resistance R. The current will flow outside like this. So in this case, what we can do is we can combine them to make an equivalent cell. How will we make the one? let's say that this is the equivalent cell and this is the equivalent internal resistance. Okay,
Okay.
now see, the cells are being connected in series means that the voltage that each one of them carries will get added up, because in series voltage will get added up. So
Yeah.
E1 plus E2 plus E3 up to n cells, and each one of them is, let's say, E only. So E1 is equal to E, E2 is equal to E, E3 is equal to E. Each one of them having the same voltage, right?
Yeah.
Because we've combined the cells that we have
Yeah.
1 volt cell, each one of them will be open. So we will have n E here, okay? And the internal resistance will also be n times R.
Yeah.
So R1 is equal to R2 is equal to R3 up to Rn is equal to R. Each one
Yes.
of them is R. This is the equivalent combination of series cells in series, okay? Cells in
Okay.
series. Now if you want to find the current that is flowing outside, I would be what? E, which is Ne, on the total resistance, NR plus R. This is the final result.
Okay.
Okay.
Yeah.
Now let's talk about the parallel combination. So cells in parallel. Now in parallel what happens is the cells are connected like this.
Yeah.
So E R E R E R, and they supply the current to a load of resistance capital R. The current, that is I. In this case, what will happen? See, each of them is connected in parallel. Then the equivalent what you can draw is something like this. There will be no change in the total value of the voltage that they will supply to the load, because in parallel voltage is same, so that will be E only, the equivalent, isn't it?
Yeah.
But in parallel, the these resistances will get added up in like this fashion, 1 by R plus 1 by R plus 1 by R up to whatever n,
And
right? So you
yeah.
will get, he is called, it's okay, not call that n, instead let call it m, because n we took for series, and let's say m terms we take for the parallel.
Okay.
So m resistances are there, then the parallel combination of them would be m by R. All right,
Yeah.
current is the same, I, then I would be equal to E upon this capital R plus m by R. Sorry, not m by R, R by m, R by m.
Okay.
This is for the parallel combination. All right.
Yeah.
Now this is for when we have the same equal value of battery connected together. But what if they are not equal? If they are, let's say, E1, E2, E3. So here E1 is equal to E2 is equal to E3 is equal to E. R1 is equal to, so this is R1, R2, R3, let's say. But if they are not equal, how will you do it? In that case, I am giving you the formula. E equivalent will be E1 by R1 plus E2 by R2 plus E3 by R3 to whatever M you go, and then divided by 1 by R1 plus 1 by R2 plus dash 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 up to whatever you have. So this will be the formula for E equivalent. This is E equivalent. Okay.
Okay.
Because they are not the same, they are different, right? And
Yes.
similarly, the formula for this term, which is, let's say, R equivalent, in that case would not be R by M only. It will be 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus dash 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 1 by whatever. Let's say we have up to R3, so 1 by R3. Should write it, the formulas.
Yeah.
So that's it up to
So the second, this one
this.
by R1 plus R2. This one is for what?
The equivalent resistance, the equivalent internal resistance.
For?
This, these
The one
all,
you just
these
said,
all
this one.
I solved by taking them equal, 1 by R plus 1 by R up to M.
Okay.
But when they are different, it will be something like this. Same thing is there.
Yeah.
It actually is the same thing, right?
Yeah.
You replace this R1 by R, this R2 by R, this R3 by R up to M, you will get the R by M only. This is the general formula. Okay,
Yeah.
this is the general formula to find this R equivalent. There are many internal resistance connected in parallel, no? So that would give us a equivalent internal resistance. Got it?
Yeah.
So that's it for today. In the next class, we will study mixed grouping of cells
Okay.
and other things as well.
Okay.
Okay, all right.